sigma minus 1 z if you're equal to 1. By using this condition here, it's easy to calculate the eigenvalues of G sigma minus 1, then to order them, and you find that the symplectic capacity of this ellipsoid is at least 1/2 of h, and conversely. So, in other words, this is equivalent to this condition, which is in turn equivalent to the general uncertainty principle. So this is a very concise and tractable form of the uncertainty principle. It's a topological formulation. And it allows you to define a coarse graining on phase space, not as people working in thermodynamics do. You know, they take small cubes and all this. Cubes is sometimes convenient, but I mean, cubes do not have any invariance properties and all that. I mean, if you transform a cube by a linear transformation, you get a parallel something. And actually, here we're talking about ellipsoids, which are much smoother. And what's inside these ellipsoids? Nothing, say. These are the smallest units, in a sense, which makes sense to talk about in quantum mechanics in phase space. It's nothing, but this nothing contains lots of information. If you calculate, for instance, the value of a Hamiltonian function on these ellipsoids, you get the ground states, the ground state energy, for instance.
I can't just say you get the quantum potential.
Can you get it from that? You can. Show me. I mean, I'm not surprised because of your paper, where it made the link between Wigner and Moyal and quantum potential. And what's the link of all this with Wigner and Moyal? To show you how easy it actually is. You see? Nothing. Okay, so now I'm going to need the pins. The Wigner transform. I think, well, this is one of the most fundamental objects in phase-space quantum mechanics. It's called also the radar ambiguity function, I think.
Yeah.
Yes. It's also called the short-time Fourier transform in time-frequency analysis, and perhaps it has even other names.
I think
Sorry?
it's called a logon in Gabor's language. You know the parallelogram guy, Dennis Gabor? He was at Imperial College a long time ago.
How do you call it?
G-A-B-O-R, Gabor.
No,
He got the Nobel Prize for holography.
Ah, Gabor! Sorry, what did you say? I know, I'm getting older. All right. Okay, let's start the variance of this. Okay, here. So I take something which is nice here. It works for psi in L2, of course, but actually, you can define the Wigner transform in Weyl calculus for psi being even a temporal distribution. So the definition is quite general. You can Wigner transform whatever you want, okay? Almost. Now, let's calculate this.
Don't try it.
No, when psi is of this form, exponential, this is a so-called squeezed coherent state, okay? Squeezed coherent state. It's a little bit more general than the fiducial coherent state and all this. It's a Gaussian. It's a complete Gaussian. X is a positive definite. This is supposed to be the big X here, the matrix X. Here, and I'm going to add, something here. Y is an arbitrary real matrix, but the X has, of course, to be positive here, because otherwise the integral would not converge at all. Well, if you calculate this here, you find that the Wigner transform of this squeezed coherent state is of this type here, okay? Where G is a positive definite matrix, which is, this is miraculous almost, which is in addition symplectic. Actually, it's quite easy to see that it's symplectic if you use the following factorization, and I forgot to write it here, wait a minute. S, we have G equal to STS, where S is equal to square root of x, 0, x minus 1/2, y, and x minus 1/2. Well, doing this, it's almost trivial to see that G is symplectic. The first one who made the calculation is a guy named Bastiaans. He works in Holland. Sorry?
That sounds Dutch.
You know him?
I don't know, the name sounds Dutch.
Yeah. He works in, I think, Eindhoven. I think he also a guy working in signal theory. You know this. And well, this is trivially symplectic. And if you do the product, you see that you have this here. Yes, but look at this here. What is G, Z, Z? This is very interesting because G, Z, Z becomes STS, Z, Z, that is S, Z, Z. Yeah, but well, okay, let's compare that with the minimum uncertainty Wiener ellipsoid, which I call quantum blobs. Basil named that the other day. Suppose I have 1/2 of m, z equal to 1/2 of h. Yeah. It turns out that m, and where m is the inverse of the covariance matrix, it turns out that this is a theorem also in symplectic geometry, that m is in this case symplectic, and that I can rewrite it like this here. So in other words, the ellipsoid defined by this condition, 1/2 of this equal to 1/2 of h bar, is just the image of a ball with radius square root of h bar by a symplectic transformation. So there's a one-to-one correspondence between these quantum blobs and the Wigner transforms of squeezed coherent states. In other words, if a coarse-grained phase space by minimum uncertainty ellipsoids is the same thing as giving all these squeezed coherent states, and we know that these squeezed coherent states can be used as an infinite dimensional basis for wave functions in L2. That's Galois analysis, as you said, and all this. So here's the link. So in other words, the uncertainty principle is a geometric statement saying that coherent states are fundamental. You know, by the way, if I take x equal to here, x equal to the identity, y equal to 0, you obtain what is called, I think in quantum physics, the minimum uncertainty state. That's exactly the reason. I mean, for the same reason we have this. But this, the symplectic camel, makes actually the link between both totally apparent. So the datum of a quantum phase space is actually equivalent to the datum of all these squeezed coherent states. So now, of course, I do not know which interpretation one can or you would like to give to this kind of quantum phase space. Can one work with that or not? There's a lady, Daniela Dragoman, who has published a paper a couple of years ago in Physica Scripta, I think. Physica Scripta, where she used my quantum blobs to propose some kind of axiomatization of quantum mechanics. I don't know how good or this is. I don't know, but there's one interesting thing here. Suppose you take the sum of two squeezed coherent states. You obtain something which is in L2. What is then the geometric interpretation? I mean, what I mean is, to a sum of coherent states should correspond some kind of set in phase space. With what? Should it be the convex hull containing the both ellipsoids, or should it be the intersection of all the ellipsoids containing those two ellipsoids? I don't know. I don't know how to add in my quantum phase space. I don't know even if it makes sense. So this I don't know. And actually I've